So we've talked about Charles' law, we've talked about Boyle's law, we've talked about Gay-Lussac's law, so we've looked at the influence on pressure and temperature and volume of gases. Now we're going to take a look at how many moles are in that sample and that influence on the volume of a gas. And that was established by Avogadro. So Avogadro's law states that two identical volumes of gas two identical volumes of different gases at the same temperature and pressure should contain the same number of moles. And so now we're saying that volume should also be proportional to how many moles are in a sample. And that volume, 1 mole, should equal 22.4 liters at standard temperature and pressure, or 273 Kelvin and 1 atm. So if I have a mole of a gas, it should occupy 22.4 liters if that sample is under standard temperature and pressure conditions. So 0 degrees Celsius or 273 Kelvin and 1 atm pressure. So what's important though is we've seen that now we can relate the volume of a sample to the number of moles in a sample, the temperature of the sample, the pressure of the sample. So many things can influence the volume of a sample of a gas. So what does that mean? Right, here's an example of that. If I have 1 mole of helium or 1 mole of nitrogen or 1 mole of methane, right, all three of those gases have a different atomic and molecular weight, but all three of those gases, if they are at the same temperature and the same pressure, and I have the same volume of all three of them, 22.4 liters, I should have 1 mole of all of those gases. I have 1 mole of helium, 1 mole of nitrogen, and 1 mole of methane. And that's what I see. Because they have different atomic and molecular weights, right? However, the weight of the sample is different. Helium is 4 grams per mole, nitrogen is 28 grams per mole, and methane is 16 grams per mole. All three of those samples, though, same volume, same temperature, same pressure, same number of molecules because of Avogadro's law, because we can relate the volume of a sample to how many moles are in that sample. So here's a question for you. And if an equal mass of each gas is put into a separate balloon, which will have the greatest volume? So assume that all of those balloons are at the same temperature and pressure. We take and just say, let's take 100 grams of each of those gases. So I've got 100 grams of helium, 100 grams of hydrogen, 100 grams of nitrogen, 100 grams of neon, and 100 grams of oxygen. Which of those 5 will occupy the greatest volume? And so we would see that for the greatest volume, I would need to have the greatest number of moles. Well, helium is 4 grams per mole. Hydrogen is 2 grams per mole. Nitrogen is 28 grams per mole, neon is 20 grams per mole, and oxygen is 32 grams per mole. Well, hydrogen has the lowest molecular weight at 2 grams per mole, so within a 100 gram sample, I would have 50 moles of that, so I would have the largest volume. Because I'd have the most moles of hydrogen, that should occupy the largest volume of all 5 of those gases under the same temperature and pressure. As I indicated earlier, we can see that volume has an indirect relationship with pressure in Boyle's law. Volume is directly proportional to temperature in Charles' law, and volume is directly proportional to the number of moles in a sample in Avogadro's law, right? As moles increase, so did volume. As temperature increased, so did volume. And as pressure increased, volume decreased. So there must be a way that we can relate all of these to the volume of a sample, right? If I put them all together, there must be some way I can put them all into one equation. And so because I have a direct relationship between moles and temperature, that goes on top, and an indirect relationship with pressure, that would go on the bottom. So if I multiply moles by temperature and divide it by pressure, I should be able to come up with the volume of a sample. And that wasn't quite right, and so we need one constant that we're going to derive to help us relate the moles and temperature and pressure of a sample to the volume of that sample. So Avogadros Law can help us determine what that constant is. So the numerical value of R, the universal gas constant, it can be derived from Avogadros Law. So I know, I just rearranged the equation from the previous slide to solve for R. What is this unknown constant that we need to let that equation be mathematically true? Well, Avogadros Law says at a pressure of 1 atmosphere, I have a volume of 22.4 liters if I have 1 mole of a sample at 273 Kelvin. So this universal gas constant R that I need to allow this equation to be true, right? Let's plug in what we have. I have a volume of 22.4 liters at a pressure of 1 atm when I have 1 mole of a sample at 273 Kelvin. So I multiply and divide. The universal gas constant R comes out to be 0.0821. Taking a look at units, nothing cancels out. So 0.0821 liters times atmosphere divided by moles times Kelvin. So our universal gas constant, that's where it comes from. It's just the remaining constant that I needed to allow that equation to be mathematically true, right? To allow us to relate volume with pressure, temperature, and moles of a sample. There are many other universal gas constants, and they just change, they just vary depending on the units. But we're going to use, because we're going to be measuring atmospheres as our pressure, and we're going to be working in Kelvin, we're going to use this universal gas constant of 0.0821. So now I have my ideal gas law, right? PV equals nRT, where pressure is in atmospheres, volume is in liters, N is my number of moles, R is my universal gas constant that we just derived in the previous slide, and T is my absolute temperature. So my temperature in Kelvin. So here's a sample calculation for you. And the biggest thing for these calculations, right, absolute temperature. So make sure temperature is in Kelvin. Other than that, right, in PV equals nRT, there's 5 variables. I would give you 4 of them, right? You're going to solve for the 1 remaining variable. So we have an experiment that calls for 3.5 moles of chlorine. What volume would this be if the gas is measured at 34 degrees Celsius and 2.45 atm? Well, my equation is PV equals nRT, and I'm solving for volume. So let me just rearrange this to solve for volume. I'm going to divide both sides by pressure. Pressure cancels out, and I'm left with volume equals nRT over P. Got a few other things to do before I can do the calculation though. All right, I've got pressure is 2.45 atm. That's fine. I'm looking for my volume, that's my unknown. My number of moles is 3.5, I know that. R does not change, so that's 0.0821 liters, atmospheres, mole times Kelvin. Temperature, I do need to convert my temperature. I've got temperature in Celsius. I need to convert that to Kelvin. So I know that Kelvin equals 273 plus degrees Celsius. So Kelvin equals 273 plus, I have 34 degrees Celsius. So my temperature in Kelvin would be 307 Kelvin. So now we can finish our calculation. Volume equals my moles, 3.5 moles times 0.0821 liters ATM mole Kelvin times 307 Kelvin, all over my pressure of 2.45 ATM. So my volume, I should have approximately 36 liters of chlorine needed for this reaction. Again, the biggest sticking point being, because we were given temperature in degrees Celsius, we had to convert to Kelvin before doing that calculation. Other than that, everything else was given for this calculation. So earlier in this semester, we've looked at the relationship between mass and moles, right? We said that moles equals the mass of the sample divided by either the atomic or the molecular weight of that sample, depending on what we were working with, if I was working with an element or a molecule. Taking a look at the gas law that we just talked about, PV equals nRT, right, where N equals moles. So we can add to this equation, we can make this equation a little bit more powerful, and we can also now find the molecular weight of a sample that we're working with. Because I know moles equals mass divided by my molecular mass, I can simply replace N in this equation with mass over molecular mass. So now we've got pressure times volume equals the mass of the gas divided by the molecular mass of that gas sample times R and T. And I can rearrange to find the molecular mass of that gas, where the molecular mass is going to equal the mass of that sample times RT divided by the pressure and volume of that sample. So really just a very powerful equation. Now we can go one step further and not only find the moles of a sample we're working with, but we could find the mass or the molecular mass of that sample, depending on the information we're given. So here's a sample calculation for you. We've got a 15.5 gram sample of an unknown gas, and it occupies a volume of 5.75 liters at 25 degrees Celsius, while at a pressure of 1.08 atm. Calculate the molecular mass of that sample. So I don't need to rearrange the equation. Already solving for molecular mass, the mass of the sample is 15.5 grams. My other knowns, I have my universal gas constant, which did not change, 0.0821 liters, atmospheres, mole, Kelvin. My pressure and my volume are also known. My pressure is 1.08 atm and a volume of 5.75 liters. And the one that I'm forgetting is temperature. Temperature, again, I need to convert to Kelvin. So Kelvin equals 273 plus degrees Celsius. So Kelvin equals 273 plus 25. So Kelvin equals 298. So my temperature of 298. So I can plug that all in. The molecular mass of this sample, 15.5 grams times 0.0821 liters, atmosphere, mole, Kelvin, times my temperature, 298 K, divided by my pressure, 1.08 atm, and my volume of 5.75 liters. So multiply and divide, and just taking a look at our units real quick, right? Grams is going to cancel out. My divide, ATM is going to cancel out. Liters are going to cancel out, and that's good because I should have, with a molecular mass, I should have units of moles per gram. So I come up with a molecular mass of 61.1 grams per mole. And again, just a nice extension on PV equals nRT, now allowing us to determine the molecular weight or the mass of a sample of a gas that we have in a reaction.